Okay, boys and girls, this is going to be a follow-up to acids and bases for AP Chemistry. We're going to look at polyprotic acids and how we calculate pH with polyprotic acids today. It's a follow-up to what we were doing in 7.2, and most of the calculations, if not all the calculations, are going to be the same. This is just a little bit of a twist on it, and so I decided to give it its own section. So without any further ado, let's get started. So we know what a polyprotic acid is because we've learned about that already. It's an acid with more than one hydrogen to give away. And so that's where we get the word poly because there are many. A common example is phosphoric acid. So notice with phosphoric acid, we've got H3PO4. And so the idea is that we can lose all three of these hydrogens, and it doesn't occur at the same time. We actually have an equilibrium that occurs at each different level. And so I've got it broken down here, and we'll see we've got H3PO4 creates a hydronium, so it donates that hydrogen, and then I'm left with H2PO4 minus. Well, I have a Ka value for this, so we're going to label it Ka1 because it is the dissociation of the first proton. The next one, we're going to take this H2PO4, it'll become a reactant, and so if you look, if we're summing up these reactions, we actually end up with reaction intermediates here. And so then H2PO4 is also going to create a hydronium ion. It's going to give away that hydrogen. And then I'm left with HPO4 2 minus. Now, again, here's where it starts to get funky on a lot of people. Notice I have a different Ka value. And so these two reactions, reaction 1 and reaction 2, happen, I won't say necessarily independent of each other, but they occur sequentially. They happen within steps, right? And notice the difference in the Ka values. This one's 10 to the negative third. This one's 10 to the negative eighth. And so we would expect this one to occur. This one, yeah, not so much, right? And so then to get that third proton off of phosphoric acid, what we do is we take our HPO4 2 minus. We have another reaction here, right? We create a hydronium ion. We release that proton, and then we're left with just a phosphate ion. So PO4 3 minus. And again, I've got a third Ka value. So for each dissociation for a polyprotic acid, you are going to have a dissociation constant or a Ka value for the release of that proton. And notice what happens to technically the strength of these acids, right? And so if I was going to rank them, I would say that H3PO4 is a stronger acid than H2PO4, which is a stronger acid than HPO4, right? Because of the dissociation constants, we can rank the strength of these polyprotic acids and their conjugates relative to each other, okay? So just again, Ka1, that would be the first dissociation. Ka2, that would be the second dissociation. Ka3, that's my third dissociation. And then I'm just left with this polyatomic ion, this proton. Or not the proton, but the ion. Okay? All right, so now what we're going to do looking on the next slide is what do we do with this information? Okay, so we understand that at each dissociation, so proton 1, proton 2, proton 3, they're going to have different Ka values. We should know from our calculations already, we can use these Ka values to determine hydronium ion concentrations of those hydrogen ion concentrations, and then we can use those values to actually calculate pH. So we need to actually look pretty logically at this because we know we've done these equilibrium calculations where we're using approximations. And so when is it okay? Because normally we say it's okay to use an approximation if we have a really small Ka value. And if we went back to that phosphoric acid example, we had our Ka1, which was a 10 to the negative third, a Ka2, which was 10 to the negative eighth, I think, and then a Ka3, which was like 10 to the negative 13th. And so they're getting sequentially smaller. And so when is it okay to use those approximations? All right. So in the, I guess, scenario 1, we would have Ka1 and Ka2 are similar, so they're relatively close to each other. And in that particular case, to calculate the pH of that particular polyatomic acid, we would need to do multiple ice tables. So we're going to use a Ka1, and then we're going to plug in some values into a second ice table, and then we'll add the hydrogen values at the end and actually use that to calculate our pH. And I'll set up an example here on the next slide, and we'll go through each one of these together. Not a complete calculation, but you'll see what I'm talking about. All right, the next scenario is scenario 2, where Ka1 is much larger than Ka2. which means, I guess another way of saying that, Ka2 is much smaller than Ka1. And that would mean that most of the hydronium or the hydrogen comes from the first dissociation. And in that particular case, we can use approximations, and we actually would ignore, we won't even set up a second ice table because the amount of hydrogen that hydrogen ion concentration that Ka2 is going to give us is going to be pretty inconsequential based or relative to Ka1. And so we can say that the pH of the solution is roughly only due to the first dissociation. All right, and so now let's go ahead and look at some examples. And so this is going to be scenario number 1, and the other one here is going to be scenario number 2. All right, so let's go ahead and check these out on the next couple of slides. All right, so our example that we're going to use here, and this is scenario 1, my Ka1 is similar to my Ka2. I'm going to use adipic acid. It's H2C6H8O4. My two hydrogens here are the acidic hydrogen, so that's why it's polyprotic, because I have two of them. And notice my Ka values are roughly similar to each other. Now, guys, I know that the 3.9s here are the same. They don't have to be the same. Really what I'm looking at to see if Ka1 is similar to Ka2 is these power of 10 values. So this is a -5 and -6. And so the exponents here are roughly close to each other. And so I'm going to say that Ka1 is similar to Ka2. It doesn't have anything to do with the numbers in the front here, the root number. It's really just looking at these powers of 10s to determine if they're similar or not. All right, so what we would have to do is there's two steps to this problem. What we would do is we would use the first dissociation reaction, and let me go ahead and pause this and write it. All right, so here's my dissociation reaction. I've got the acid plus water gives me my hydronium plus my conjugate base here. And so the question becomes, like, let's say that we have, for example, a 1 molar solution of this. We would want to figure out the pH, and so what we'll do is we'll use an ice table for this first dissociation, and we can actually solve for the equilibrium concentration of my hydronium right here, right? And so we would need the H3O plus concentration at equilibrium, and this is based on Ka1, and so that would be based on Ka1. Well, that's a subscript there. So Ka1. And this is essentially just taking and using my ice table and doing my calculations like I know how to do them. Not too crazy or anything like that. What I'm really interested in showing you guys here is what we would do with this second Ka value. And so let me go ahead and pause this and move the slide up. Okay, so with the Ka2, what we're doing is we're looking at the second dissociation reaction, and again we're going to set up an ice table, and we would get, and this is the tricky thing, the concentrations that we've got this concentration and we've got this concentration because those are the products of my first dissociation reactions, and so the concentrations that I would get in these would actually become these concentrations, right? And so when I set up my second ice table, that's where I get my values from to stick everything in. All right, and so I would have to actually solve the first ice table, and then I would use the values of my hydronium and my conjugate base, and then I would stick them into the second ice table, and I would get a second value of hydronium. And this is what I'm really concerned with, is this value right here, because, and I'm going to go ahead and call this like number 2, and this one up here would be number 1. And so when I solve for the pH, I need my overall H3O plus concentration, and that's going to actually equal number 1 plus number 2. All right, and so I would have to take both of these values, add them together, and that would give me my complete and total, or my total hydrogen ion concentration in solution. And so that's the only thing. It's still, I know it seems a little bit confusing, but I think as soon as you guys do the first example on your own, where you'll set up the ice table, you'll solve for these values here, then you use these values, right, because these are actually in solution, and this reaction, this second dissociation is occurring in this environment, we would have to use those initial values to to give us our overall, and then we'd have to total up the two hydronium concentrations at equilibrium to come up with our pH. All right, so that's the one twist. The second scenario that we're going to look at here, and let's go ahead and move slides and get to that. All right, so my second scenario here is when my Ka1 is much larger than my Ka2. The example I'm going to use is carbonic acid. And so I've got H2CO3, so I've got a Ka1 and a Ka2 for each of those protons, those acidic protons that are going to dissociate. Now notice again, I'm not looking at these root values here. I'm looking at the powers of 10s, and so I've got a -7 and a -11. Now, I use this example because this is kind of a borderline example. And this probably represents a difference of 4 here in the Ka values. A difference of 4 would probably be my lower limit of when I would use scenario 2. Normally I'm going to end up with something that's, you know, like, hey, say this is -2 and this is -19. In that particular case, you definitely know it's easy to make that decision. But I wanted to, in the example I showed you in the lecture, give you kind of your lower limit. And I would say a difference of 4 here between Ka1 and Ka2 would be my lower limit of when I would use scenario 2. Anything more than that difference of 4, you're going to definitely use it. Anything less, you'd have to go back to scenario 1 and actually do multiple ice tables. All right, and so essentially what we're going to do is I'm just going to draw this out while we're on here. I've got my H2CO3 plus water, and so this is my first dissociation. And what I want to show you is that this occurs, right, based on the -7th, and so I'll get some equilibrium value here. And then when we move to our second dissociation, I've got HCO3 minus plus water gives me H3O plus, there's a plus up there, plus CO3 minus 2. And so what we're going to say is that when I'm doing my pH calculations, I'll actually use this value. So I would use the ice table to solve for that first hydronium ion concentration. And then normally what we would do if these values were close to each other, then we would use both of these values, plug them into the second ice table, and then proceed on and calculate the hydronium concentrations and add them together. But what we're going to say is through approximation, we're going to ignore this second dissociation because we were going to say that the amount of hydronium that we would get, so the amount of this hydronium that we would get is so small relative to the amount that we're going to get from this first dissociation that it's not going to affect the pH significantly. All right, and so we would just do the first ice table, use this hydronium ion concentration to plug into our pH calculations and solve for the pH. All right, and so a lot of people like scenario 2 more than scenario 1 because we can ignore all this second ice table and third ice table and all that other jazz. We just do our first calculation for our first ice table to solve for this concentration, and then we're done. We use this concentration to plug into our pH calculations. All right, so be familiar with the scenarios. I know there's probably some questions to go along with this, so come to class with that, and be ready to and I guess attempt to solve those problems as well. And you'll see once you start solving the problems, it's not as complicated as you would think. But a lot of people are intimidated by this type of calculation, and really in reality you shouldn't be, because you already know how to do all the math, you know how to do the ice tables and set them up. The real question is just where do you get your values from? All right, so come to class with any questions, attempt to do the problems, and we'll see you there.